We present a novel approach for fabricating tendon-driven robotic systems. Particularly, we demonstrate that a biomimetic finger featuring accurate bone geometry, ligament structures, and viscoelastic tendons can be synthesized as a single part using a multi-material printer as shown here. The typical process for creating a robotic platform often consists of designing and ordering custom parts and time-consuming assembly. The proposed design process for a single print robotic platform relies on a multi-material printer, which eliminates the need to construct an interface between the rigid skeletal structure and tendon system. The CAD model of the finger design features bio-inspired anatomical features vital to replicating motions of the human finger. The model contains printable designs for the distal, middle, and proximal phalanges, articular cartilage, collateral ligaments, volar plates, annular pulleys, flexor tendons, and common extensor mechanism. This design is printed as a single part where the bones are rigid and the ligaments and tendons are flexible. The artificial muscle required to drive the printed tendons of the finger can also be printed in place. The resulting robotic platform is difficult to model analytically, so the proposed CAD design was imported to Mojoko, a physics simulation environment which can be used to construct controllers and to optimize the interactions between the musculoskeletal structure, tendons, and actuation. The simulation results were validated using an in-house developed test rig. It was found that 3 actuation elements are sufficient to control the finger's kinematics and dynamics, and Mojoko simulations are similar to the experimental measurements.